Hello again, everyone. Thank you for joining us in the last video in this series. So again, please like, subscribe, share, give us your input on all that we're doing. We really appreciate your feedback. So previously, just a suggestion. If you haven't seen the first video in the series, please check it out. We talk about mirror terminology, concave and convex mirror terminology, and sign convention. Then we did 2 videos analyzing the object as it sits outside and inside a focal point of a concave mirror. And then we did a video with a couple of exercises. And now we're going to do 3 exercises in this video and wrap up the series on concave mirrors. So let's begin. So we have an object that produces a virtual image 48 centimeters away from it. So if the image is 30 centimeters away from the concave mirror, what are the focal length and magnification of the mirror? So here's a mirror. Here's an object. Here's an image. It's a virtual image, so it has to be on the dark side. So now we know this distance is 48 centimeters. If the object is 30 centimeters away from the image is 30 centimeters away, then the object has to be 18 centimeters away. And it makes sense because this is less than that, right? 18, dO, is less than absolute value, di. Again, we talked about that in one of these videos. You have to be cognizant of that the image, virtual image, is basically farther away from the lens than the object. All right. And now let's write down what we know. We know that d sub O is 18 centimeters, it's positive, and d sub I is negative 30 centimeters because it's a virtual image. Okay? So everything else now is, F is easily computed from the thin lens equation. And the magnification is simply computed from di and do. So let's go ahead and do it. 1 over F is 1 over do plus 1 over di. Common denominator, do di, do plus di, flip, let's plug them in. Do is 18, so F 18 times negative 30 over do is 18 minus 30. That's exactly what I was talking about. F has to come out positive, so the top and the bottom have to be negative. So in this case, because this is negative already, so that is 18 times negative 30 over negative 12. So the negative cancels out from the top and the bottom. Divide by 4, or divide by 6. So here's 2, here's 5. And 18 divided by 2, 9 times 5 is 45 centimeters. So the focal length is at 45 centimeters, okay? And positive. And obviously, the object is inside it. That's how we produce the virtual image in the first place. So now the magnification is negative di over do, negative. Di is negative 30. Do was 18. So the plus, and let's divide by 6 top and bottom. So this is 5/3. Okay? Magnification is a bit bigger. So the image is a bit bigger than the object. You know, this is basically 1.6667. Okay? So let's do the ray tracing. Here's the object. I put it at 18 centimeters. The image is 45. So let's, again, array, parallel, goes through the focal point right here. Array through the center, bounces back on itself. And then array through the focal point comes out parallel. They don't meet here. They meet on the other side. Here's the extension of the blue ray. Here's the extension of the reflected green ray. And here's the extension of the orange ray. And they meet all over here. There it is. Here is the image. It's almost twice as large. Right? It's 1 point. This is 2. So we can go here. M was 5/3, right? Is HI over HO. So HI is 5/3 times HO, which is 2. So that's 10/3. Right? Which is 3.33, which is roughly 1, 2, 3. You can say it's roughly 3.33. Okay? And again, this is DO. This is DI. This is F. So again, each is 5 units. So the object is 18, so that's 15, that's 20, and it's roughly closer to 20. So DO is 18, again, roughly closer to 20 than to the 15 right here. Okay. And that's problem 1. Again, this matches, basically corroborates the results we got from the lens equation. All right, so here's the second problem. We have an object 2 centimeters tall and 36 centimeters in a concave mirror. So H sub O is 2 centimeters, and so D sub O is 36 centimeters. Produces a real image that's 1/2 centimeters tall. So H sub I is 1/2 centimeters. Where's the location of the image? So I want D sub I, and I want F. That's what's given. That's what I want to find out. So let's first find out D sub I. So I don't know what F is, so I cannot use that equation, this equation right here, to get D sub I, because F is unknown. So I got to use the magnification, or H sub I and H sub O. So here's what we know. M is negative D sub I over D sub O, which is H sub I over H sub O. And by the way, let's fix H sub I real quick right now. Object produces a real image, so it is inverted. So if it's an inverted image, H sub I is negative. Okay? It's pointing opposite to what the object is. So I want to get now D sub I. So D sub I is negative D sub O H sub I over H sub O. Just cross multiply here. Now plug numbers in. Here's the negative. D sub O is 36. H sub I is negative 1/2. H sub O is 2. So that's like 36 over 4. The negatives cancel out, or 9 centimeters. So D sub I is 9 centimeters. Now I know what D sub I is, and I know what D sub O is. I can get F right away. So 1 over F is 1 over D sub I plus 1 over D sub O. And again, the same math as before will give us, check the previous videos, D sub I, D sub O, D sub I plus D sub O. Okay? Again, see previous videos. So now, D sub I is 9, D sub O is 36 over 9 plus 36, which is 45. So here and there gives me a 5 down here. So I get 36 over 5, or 7.2 centimeters. Okay? So I get 7.2 centimeters for the image height. Sorry, for the focal length. The image height is a half a centimeter. It's real. And the image location is at the 9 centimeter mark. So let's see. Here's the object. Here is the focal point at 7.2. So 2, 4, 6, roughly, right there. Here's that. So the first ray is parallel to the axis, bounces off through the focal point. The second one through the center, bounces back on itself. And then the third one through the focal point, bounces out parallel. And the image should be right here at the 9 centimeter mark, right? So this is 8, this is 10, so that's roughly 9. And there it is. Confirmation of the stuff we did with the of the analysis we did using the thin lens equation. All right, on to the last problem. So we have an object, it's away 20 centimeters away from its real image and 2 times as large. So let's first consider this situation. There's DI, there's DO, and the distance between them is 20. So DO minus DI is 20. And what kind of mirror we're using? We're using a concave mirror. Okay? Only a concave mirror will produce a real image. Now the object is twice as large as the image. So the magnification is -1/2, because that is negative DI over DO. Okay, the image is half the size of the object. So basically DI or DO, you can cross multiply, is twice DI. And let's go ahead and plug them in. So now this can plug in into here, right? So DO, which is twice DI, minus DI is 20. So 22 DI minus DI is just DI, which is 20. So DI is 20. But DO is twice DI, which is 2 times 20, which is 40 centimeters. So just from this information that we were given, we were able to find DI and we were able to find DO, okay? And for this configuration, and we got DO to be at 40 centimeters, DI to be at 20 centimeters. And now this will allow us to compute F, because again, we start with the lens equation. And then, again, look at the previous videos. We can rearrange, get a common denominator, rearrange, and we get this for F. So DI is the 40 times the DO, which is the, let me see, DO is the 20, is the 40. DI is the 20 over 40 plus 20. So it would be 40 times 20 over 60. This cancels out. And then here, gives me with a 3 and a 1, which is 40 over 3, which is roughly 13.333, and so on. Okay? Now, this is this configuration. But what if someone comes and says, hey, what if the eye is actually on the other side? It's a real image after all. You know, what if I have this situation? Obviously, F is here somewhere. The distance between them is 20 centimeters. Can this happen? Well, let's go ahead and write it out. Since the distance is 20, and for this configuration, it tells me that this is DI right here, right? This is DO right there. DI minus DO is 20, because DI is farther out. And I know the magnification is negative a half, which is negative DI over DO. Again, that was given. The object is 2 times as large, so the image is half the size of the object. And since it's a real image, the magnification is going to come out negative. So now DO equals 2 DI. So now I plug things in here. DI minus 2 DO, 2 DI, because DO is twice DI, is 20. So DI minus 2 DI, that's negative DI, equals 20, or DI equals negative 20 centimeters. But that is a contradiction. Right? Because we said, first of all, it's a real image, so the eye has to be positive, and here we came out negative. What this is telling me is the eye is over here. Okay? Which is not correct, because it's a real image. So this scenario will never happen. You can never have DO inside the eye. So the image, this is the scenario that will happen. The object is out, and then the image is in there. Okay? And let's see how this works out. See, here's the object is out. The image has to be in here somewhere. Here's the focal length. Here's the radius. Here's the object. A parallel ray goes through, hits the mirror, bounces back to the focal point. Ray perpendicular through the center, bounces back on itself. And then the third one goes through the focal point, comes out parallel. And then the image is right here. It's 1 centimeter versus 2, which is basically a half. And it is roughly at the 20 centimeter mark. Okay? The object is at the 40 centimeter mark. There it is. And that, again, is a confirmation. So whenever you're given something like this, the distance between the object and the image is some number. Think about it a little bit more. Think maybe there's another scenario than just image on the left, object on the right. Maybe the image is on the right and the object on the left. Okay? So give it some thought. The math usually will work out properly. And then, of course, you can have the lab to just verify that if the object is out, the image is smaller when it's to its right. Okay? And that's all. Thank you for joining us for this series. And the next series in optics, we'll do convex mirrors. All right? thanks again, and we will talk. I'll see you hopefully in the next series, either math or engineering or optics. Take care. Bye.